Okay, so let's take a look at question number 2. And so in question number 2, we've got a random variable x, which has CDF that will denote capital F of x. And now what we're going to do is we're going to pick a random sample of n values independently from this population. And rather than calculate the mean or proportion of those values x, we're just going to take a look at, out of those n values that I pick, which one is the maximum. So x max is going to equal the maximum value in the sample of n different values. And so what we might want to think about is, well, how can we describe this distribution? Okay. So let's take a look. So if I were to say, for example, what is the cumulative probability that the maximum value of x in my sample of n values is a, well, then what that means is every value of x that I pick should be at most a. So in other words, this probability that x max is less than or equal to a would be the probability that each of our individual x's is less than or equal to a. And because we're picking independently, each value of x that we pick is independent of the previous one, that means this probability we can calculate by taking the probability that x1 is less than or equal to a times the probability that x2 is less than or equal to a, all the way up times the probability that xn is less than or equal to a. And since each of these x's are being picked from the same population, from the same random variable x, then this is just a probability that random variable x is less than or equal to a raised to the nth power, since each of these probabilities up here are all going to be identical. And this over here is just exactly what the cumulative distribution of x would be, not x max, at a, right? Since when we say fx of a, by definition, this is the cumulative distribution. This is saying what's the probability that x is less than or equal to a. So we can plug that in over here and raise that to the nth power. So this would exactly give us the cumulative distribution for x max. Okay, so that answers question 2. Moving on to question 3. Now we want to use this cumulative distribution we found to figure out what the PDF, the probability density function of x max is. So just notice here, I'm using a as the input into this function because I don't want to use a lowercase x. I don't want to get that confused with the capital X. So in general, the relation between a PDF of a random variable and its CDF is that it is the derivative of that CDF. So for us, what we want to do is take the derivative of the CDF that we found in part 2, question 2. So I want to differentiate fx a raised to the nth power. And so here we can use the power rule on this. The n comes down. We get cumulative distribution of x at a. Power drops by 1, but we need to be careful. Here we need to use the chain rule, so I would actually then need to multiply by the derivative of the inside function. And if I take the derivative of the CDF of random variable x, then again, by definition, that would just give me, so I'm going to copy this down over here, and taking the derivative of the CDF above, that would just give me the PDF of random variable x. So here I've got the PDF for x max is related to both the CDF and PDF of the random variable x. So let's see how we can now use this in an example like question number 4. So now in question number 4, I've got x, it's a random variable, uniformly distributed between 0 and 1. And ultimately what we want to figure out in part B is how likely is it that x max is greater than or equal to 0.9. So just to kind of motivate where we're heading with this, what we'd like to calculate is what's the probability that x max, in this case, is greater than or equal to 0.9. So what we can see from parts 2 and 3 is that this is going to require us to figure out what the CDF of x max is first. And that's going to depend on what the CDF of x is. So for uniform distribution, just to kind of back up for a second, that would mean that for x values between 0 and 1, they all have the same likelihood of occurring. So f of x should be constant for all of these values since they all have the same likelihood of occurring. And if we want this area underneath the PDF to be 1, then we can see that the height of this region should be 1. So long story short, the PDF here is equal to 1 as long as x is between 0 and 1, and it's going to be 0 otherwise. And then to find the CDF, the CDF would be the antiderivative of the PDF. So we could integrate that and get x as long as x is between 0 and 1, and it's going to be 0 if x is less than 0, and it's going to be 1 if x is bigger than 1. So that would be the CDF, and again, that's going to be useful when we want to calculate the CDF of x max. Okay, so now coming down to part B, we wanted to calculate what's the probability x max is less than or equal to 0.9, and so this would equal 1 minus the probability that x max, for example, is less than 0.9. So I'm going to use this because this probability right here is exactly the value of the CDF of x max at 0.9. So now we can say this is going to equal 1 minus the value of the cumulative distribution of x max at 0.9. Okay, since again, by definition, that's what it means when we calculate the value of a cumulative distribution function at a specific value. It's saying, how likely is it that x is less than that value? So now we would get 1 minus, and here f max, what we saw in question 2, would just be f of x, f sub x, excuse me, at 0.9 raised to the nth power, which in this case is 10. So this is what we saw, this is what we proved in question number 2 above. So now we've got 1 minus, and fx, we saw over here, is just equal to x. So fx at 0.9 is just going to equal 0.9. And then we raise that to the 10th power. And then simplifying all of that is going to give us 1 minus 0.3487, which gives us 0.6513. Okay, so if we pick the sample of size 10 values out of a uniform distribution from 0 to 1, what we can see here is there's about a 65% chance that the maximum value is going to be 0.9 or bigger.